abrir el tema. Te voy a empezar a hablar en inglés. Starting from now. Ready? Okay. Let me open this because this is the presentation. Okay. Oh, yeah. The idea is to talk about the big O notation. The big O notation is a notation from discrete mathematics that we use in order to compare algorithms. When we compare algorithms, we compare the function that describe how many instructions the algorithms need to run in order to process any data. Then I'm going to talk about this topic. Okay? First one, the idea is try to introduce this with this question. For example, this question is very simple. Here we have a square plate with this mass, 100 kilograms. And what about knowing that we can estimate maybe the mass of this square, right? For example, if this square here is 100 kilograms, what do you think that is the estimation for this plate that we have here? It's the same material?
The same square is
Exactly.
400 kilograms.
400, exactly, because you can see that is
Yes.
4 times, and one multiply, one product, 4 times the square of that, exactly 400. Yeah, this is that we can estimate here, but in this case, it's not easy, because the shapes they have a regular form, but if this, for example, have 60 kilograms and this one is 20 and 20, about that, we can estimate maybe how is the mass of this figure. Maybe duplicate the figure. Duplicate that. Or can be the same, no? Exactly. Because this one have 4 times this one. This one can be here, 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 and here.
Is 240.
Then it is 4 times of the other square. Exactly. We can estimate, not exactly. It's not exactly, but we can say, okay, the upper bound, the upper bound is 240.
Yes.
It's 240.
Yes.
It's not exactly because we know that we have empty spaces, but this is the maximum quantity that we can say this is the mass. Because exactly, we can only say that it's 4 times the first figure. This is the same thing that we are doing with big O notation. Because in big O notation, the same happened with this one. We estimate using the maximum quantity, the upper bound, and for the reason is 240. In this one the same. Okay, we can estimate the volume of this cube, supposing that are made of the same material.
800 kilograms.
800 kilograms. Because this is 8 times
Yes.
this cube. Exactly. This 8 times that, and then you have 100 times 8, 800. Yeah, exactly. This is an estimation because it's a regular form. No? It's a regular form, it's a cube, but in this case, it's not exactly because it's an irregular form. In this case, the figures have a different, but we can estimate the maximum. We can estimate the upper bound. In this case, if this one that is with 10 meters, the mass is 1,000, then how we can estimate that is the mass of this statue?
3,000. Estimate 3,000 kilograms.
What?
3,000
3,000?
kilograms.
3,000 because, okay,
Because
maybe
it's three statues.
3 times the statue of the big, the smaller statue. This one is 3 times exactly. is scale 3 times. It's not exactly. It's not exactly, but we can say that is the maximum, no? It's the upper bound. It not will not be greater than the 3000. This is the same that we use with complexity. Because when we compare complexity of the algorithms, we are comparing a function that defines the type complexity or the space complexity. As I said a little bit moment, the type complexity regarding to the instruction, how many instructions the algorithm need to run, and this one is regarding to the memory, how much memory need to the algorithm use for say the data. For times, we need to compare the operations, comparisons, the number of repetitions, and for the space, we only use the data structures, the types of the data structure, because depending of the type, if the quantity of the space that the variable need to use in the memory. An integer need a different space than a chart. Then, depending on the data and the type of the data is that space. But this is a problem that is easy to solve because we can buy more memory. This one is difficult to solve because in the time we can't do that. We cannot buy more time. We just have 1 second, 2 seconds. Then for us, we are concentrating in this complexity, in time complexity. But how can I do that? We have an algorithm, then we need to count how many instructions need the algorithm run to process n data. Then, for example, if this is the algorithm, this instruction execute what time, this instruction execute what time, but this one, the other instruction that have into the loop, they will execute any times. They will execute any times. Then, if I sum the instructions, we can define a function like that, because this is the number of the instructions that we have into the loop, and this is the number of the instructions that we have alone. For example, this one that is only one time, this one, and this assignation. Then, for every algorithm, we can have a function that defines how many instructions we need for process any data. But we don't compare functions per se. I mean, we don't compare, for example, the complete function. We need to use another notation in order to approximate this function to a big function using a notation. For this one, to compare functions, we use this notation, the big O, that is regarding to the upper bound, the maximum. The omega is the lower bound, the minimum. And this is when the two functions grow in the same rate. Rho equals. This is equals, this is less, and this is greater than. This is the upper bound. Then we use the functions, that is the number of instructions for this algorithm, and we need to use this to classify. For example, depending on the function, we classify the function if this is in this order, logarithm, or if in this order linear, or if it's in this order exponential. Then we use this notation to classify the function of the algorithm. In other words, that we do is an approximation. The approximation is not the function exactly. The approximation is use the upper bound, the maximum. Then we compare the maximum, the upper bound. This is what we do. Compare the big O notation. For this reason, this is the notation that is used in computational complexity, when we need to compare the efficiency of algorithms. This is hard. This is the idea with this presentation in English, try to talk about the big notation. But now that we will do is try to do some exercises, but these exercises will be in Spanish, yeah, in order to understand better the concept, the definition. Ready? Then we will now continue in Spanish. Thank you.